Our everyday intuition about motion is deeply flawed. Because we live in an environment dominated by friction and air resistance, we naturally assume that continuous force is required to sustain velocity. We think things need a push just to keep moving. To understand true physical laws, we have to conceptually strip away that environmental noise and isolate an object completely. Today, we are examining the core principles of classical mechanics. We will analyze force, inertia, and the mathematical rules that govern physical interactions. Isaac Newton first formalized these principles in 1687, laying the groundwork for how we calculate motion today. We must begin by strictly separating two concepts, mass and weight. Mass is an intrinsic scalar quantity. It is a measurement of an object's inertia, or how much matter it contains. Weight, however, is a localized gravitational force vector acting upon that mass. If you place a block with a mass of 10 kilograms on Earth, the acceleration due to gravity causes it to exert a downward force of 98 newtons. Take that exact same block to the Moon. Its mass remains exactly 10 kilograms, but because the Moon's acceleration due to gravity is roughly 1/6 of Earth's, that 10-kilogram mass now weighs only 16.3 newtons. This distinction explains the weightlessness astronauts experience in orbit. The Earth's gravity is still acting upon them, but because their spacecraft is in a perpetual freefall, their apparent weight disappears. Their mass, and therefore their inertia, remains constant. This brings us to Newton's first law, the law of inertia. An object at rest remains at rest, and an object in motion remains in motion, unless acted upon by a net force. An object requires exactly zero net force to maintain a constant velocity. Mastering physics requires overriding our Earth-biased intuition. Force does not create motion. Force only creates changes in motion. Let's return to our isolated block in the void. We know what happens when there is zero net force. What happens when an external force is introduced? Newton's second law dictates that an unbalanced net force acting on an object determines the rate of change of its velocity over time. We represent this with the formula F equals ma. Applying a force vector to a mass generates a corresponding acceleration vector. The relationship is directly proportional. If you double the force, you exactly double the resulting acceleration. The relationship to mass is inversely proportional. If you double the mass of the block, that same force will only yield half the acceleration. A higher mass means a higher resistance to being accelerated. Because force and acceleration are vector quantities, there is a strict rule here. The acceleration of an object will always point in the exact same direction as the net force causing it. In two-dimensional space, we can break these vectors down into independent x and y components. This allows us to track vertical and horizontal movement independently. In reality, objects rarely experience just one force. When multiple angled or opposing forces act on the same object simultaneously, we must calculate their mathematical sum. That sum is the net force. Acceleration is not a force. It is a measurable change in an object's state of motion. It occurs only when the sum of all forces acting on a system does not equal zero. Let's take our block out of the pure void and drop it onto a physical surface. This introduces real-world environmental interactions. To map these interactions, physicists use a free body diagram. We simplify the object to a single central point and draw the forces acting upon its vectors from that center. We start with the downward pull of gravity, representing weight. Newton's third law states that for every action, there is an equal and opposite reaction force. Because the block's weight pushes down into the surface pushes back up. We call this the normal force, and it always acts directly perpendicular to the surface of contact. Do not assume the normal force is automatically equal to gravity. It is a reactionary contact force. If you are standing in an elevator accelerating upward, the floor pushes harder against you, increasing the normal force, even though your true weight remains unchanged. If we apply a horizontal pull to our block, a new reactive force appears. Friction pushes in the opposite direction, actively resisting the relative motion between the two surfaces. We distinguish between static friction, the threshold force required to hold an object completely still, and kinetic friction, the weaker force that resists an object once it is actively sliding. Unwanted kinetic friction saps mechanical energy. engineers spend vast resources trying to manipulate it, using ball bearings to force complex systems to operate smoothly. The free body diagram acts as our primary analytical tool. It takes the messy reality of physical contact and collapses it into predictable, solvable geometry. We can scale these principles up to analyze connected systems where multiple masses interact with one another. The Atwood machine is the classic test of tracking forces across a system. It consists of two unequal masses connected by a single string draped over a pulley. When force is transmitted axially across a cable, it is called tension. Assuming the string is massless and the pulley is frictionless, there is one primary rule we must follow. Tension is identical at all points along that string. To solve the system, we first isolate mass 1. Its free body diagram reveals tension pulling upward and its own weight pulling downward. Next, we isolate mass 2. It experiences that exact same upward tension force, but a much larger downward weight force, pulling the entire system in its direction. Because the masses are tethered, they share the same magnitude of acceleration. When we add the individual force equations together, the positive tension from one side and the negative tension from the other sum to 0. This leaves only the external weights to determine the net acceleration of the entire system. Regardless of how complex a physical machine appears, decomposing it into individual free body diagrams reveals the predictable mathematical equations driving its motion. Gravity and tension act as constant, sustained forces. But physical mechanics must also account for instantaneous forces. During a collision, contact forces are not sustained. Instead, they spike dramatically over a very short time frame of just milliseconds. To analyze these impacts, we use linear momentum, which is an object's mass multiplied by its velocity. Momentum quantifies an object's total amount of motion. To actively change an object's momentum, you must apply an impulse. Impulse is the force applied multiplied by the specific time interval over which it acts. This gives us the law of conservation of linear momentum. In a closed system, the total momentum immediately before an impact exactly equals the total momentum immediately afterward. We divide collisions into two types. In an elastic collision, kinetic energy is perfectly preserved. In an inelastic collision, some kinetic energy is permanently lost, converted into heat or physical deformation of the objects. The individual forces experienced during a crash are violent and chaotic, but the total momentum of the closed system remains an unbreakable mathematical constant. Let's bring these rules together into a practical, exam-level problem to see how these theories operate in practice. This diagram shows a 10-kilogram block resting on a rough surface with a kinetic friction coefficient of 0.2. It is being pulled to the right by a string exerting 50 newtons of tension. Step 1 is translating the physical objects into a pure free body diagram. We map the weight pulling down, the normal force pushing up, the tension pulling right, and the kinetic friction pulling left. Step 2 is isolating the y-axis. The 10-kilogram block has a downward weight of 98 newtons. Because it isn't moving vertically, the upward normal force is also 98 newtons. We multiply that normal force by our 0.2 coefficient, yielding a kinetic friction force of 19.6 newtons to the left. Step 3 is resolving the x-axis. 50 newtons of tension pulling right minus 19.6 newtons of friction pulling left leaves a net force of 30.4 newtons to the right. Applying F equals ma, we divide that net force by our 10-kilogram mass to find our final acceleration, 3.04 meters per second squared. When solving these systems, watch for common pitfalls. Remember that weight is an external force acting upon an object, not an internal property. Never conflate mass with weight. And in momentum problems, always account for your vector directions with correct positive or negative values. Translating physical contact into mathematical vector diagrams provides the precision required for engineering. It replaces qualitative observation with a rigorous predictive framework.